Great. So we're going to talk a little bit today, more specifically about online programming assignments, in particular how they were done in Coursera in the 4 courses I created for FPGA design. Involves auto grading and Dockers and some other things, some of which I didn't know anything about before I started this process. So I'm hardly an expert, but I have gone through it once or twice at this point, and hopefully some of this information will be helpful to you if you're going to try to do a similar sort of thing. So let me see if I can get, there we go. So just by way of introduction, who I am, as William alluded to, I've got prior experience teaching many years ago at the School of Mines in South Dakota. That's how I kind of got started with all of this. But in the in-between time for over 25 years, I was a design engineer, an engineering manager, director of engineering. Found out that I didn't really like management as much as I liked engineering. And so kind of went back to that and then eventually back to teaching again. So I've kind of gone through the whole cycle, if you will. I've been here for 7 years. Way back when I spent a few years at the School of Mines. These are a list of my interests. I've worked in a lot of different industries, and that's given me kind of a broad range of experience, which I think has been helpful for my students, and also helpful for lots of different kinds of examples that I can use in my classes. I'm married with 2 kids who both think that they're smarter than I am, and they're actually both pretty smart, so they're probably right about that. So FPGAs on Coursera. This is a specialization that I created. This kind of shows you a little bit about how it's done. It's been much more popular than I anticipated. So over 90,000 learners in all 4 of the courses together. These first 2 have most of them. That's where the 72,000 learners comes from. You look at that, that's the number of people who actually have started the course. The number that finished is much smaller. But even at that, over 5,000 people have completed one of these courses in the specialization. And so that provides a lot of impact and a lot of feedback for us. And I've used some of that information to help improve the on-campus courses. So I think it's the sort of thing where the online courses kind of help improve the on-campus ones, and then I use stuff from the on-campus ones to improve the online ones, and they're complementary to each other, I think. The FPGA specializations offered for free, so you can audit it and you can watch all the videos and do the homework if you want. It won't get graded in that case. If you want it graded, you have to take the certificate path for $99. Then you can get a certificate saying that you've passed this course and so on. And then it's also part of the University of Colorado MSEE online on Coursera. And so that's what's being offered now, that this is what made me learn a little bit about programming assignments and how to auto grade them. So for these particular set of courses, they have a global reach. 48% of the students are from Asia, 22% from North America, 19% from Europe, and then the rest from the rest of the world. This has been a really interesting thing to put together. So kind of as a first question for everybody to think about, how is online education different from in-person on-campus education? And in particular, I'm thinking about online education on the Coursera platform using a MOOC. Just how do you think it's different? presenting the same material, but the avenue by which it's delivered is different, and that has some consequences, I think. So let me suggest a few things that are kind of unique about doing online education. One is that you're going to have less interaction with the instructor. So structured feedback's often included in an online setting. You know, on campus, if you give them a homework assignment or if you give them an exam, you can grade the exam and you can write in red ink all over the exam with all sorts of feedback, and then they can learn from that. But you can't really do that in an online environment very effectively. And so you have to kind of examine what they've done and provide some feedback in a more automated sort of way. Everything that you do online, in fact, including lectures, labs, assessments, and grading, all has to work at a large scale and be easily scaled. So HP talked a lot about how you create content for the lectures and labs and so on online last time. This time, then we're going to talk about kind of the other half of the job, which is all the assessments and the grading. You know, when you're putting a MOOC together, I had the experience at least that when I got all the videos done, then I was like, whew, I'm done, right? Only to discover that I was really only about halfway done, because now I still had to create all the assessments. And particularly when we got to the online degree, how do we grade everything in a way that's consistent and also secure in some sense? And so we've got to find a way to scale all the assessments and the grading. In particular, the assessments have to have a way of being auto-graded when they're online, as grading thousands of submissions manually is just not practical. But it's possible to do this in a way and get very similar to results to the grading that you do on campus in person. And at first blush, it might seem like, well, you know, it's never going to be quite the same, and it maybe isn't quite the same. But we've been able to do this, and we found that we are getting a very similar statistical distribution of grades when people go through my on-campus FPGA course and when they go through the online specialization. Grading curve looks almost exactly the same. So we think that the assessments are providing us with a good evaluation of what people have learned as they're taking this course. And so it is possible, I think, to achieve that, even though, again, things online are a little bit different. So to get more specific then with programming assignment, assessment, objectives, and challenges, we kind of had these in mind when we were first creating the auto graders for some of our programming assignments. First of all, we wanted the assessments to be fair and consistent, provide an accurate evaluation of student work, you know, and be done in such a way that it doesn't matter who the student is, you know, where they're from, where they're located, that it would tend to treat everybody the same way. And I think, you know, particularly in our case, it's because programming work is so objective in general that we're able to do that. The assessment should provide some significant feedback so the students can learn from the feedback that they get and improve, so that when they do the assignment again, and in some cases, you know, they're allowed to do the programming assignment multiple times and submit that until they get to the point where they've gotten everything correct. And then lastly, assessments should be secure, so that cheating can be eliminated or at least made more difficult. And this is a bigger challenge, I think, in the online environment. than it is on campus. And so we've kind of had this in mind as we've created some of these programming assignments. So these are kind of three of the challenges or the objectives that we had when we were working on this. So did I forget anything important here? Is there anything else that should be added to this list of assessment objectives? I think I probably,
Tim, I'm just thinking the thing that's incredible here is that it's how many thousands of students did you total out? 90,000 students? I mean,
yeah.
the auto grading, that this all has to work through auto grading is, it's kind of amazing. Anyway, onwards.
Yeah. There's a lot of different ways to do auto grading. In my first course, I used some multiple choice quizzes, which is okay for some content. Coursera's got a fairly good quiz authoring tool that allows you to do a lot of different types of questions. You can have numeric answers. You can use regular expressions. They also have peer grading, which I did in the first course for some of the project submissions that had to be turned in. And although that works, that's the one thing I got the most complaints about from students. And as you might imagine, they didn't like the way their peer grader graded their assignment when they turned it in. I've since come up with a way to take projects and auto grade them so that the peer grading maybe isn't necessary in all cases for these kinds of assignments. And certainly with programming, there's a way to do auto grading. And so we'll look at some examples of that. Okay, so scaling programming assignments. Within Coursera's platform, there's a couple of different ways in which you can grade programming assignments on a large scale. The first one is they have a set of tools that you can use directly. So they have a number of different tools, and I can't remember them all. And it turns out I didn't use any of them myself. So, these tools apply to programming in C or Java, and they might have support for some other languages. I know they had that in the queue at the time. And so as long as your programming assignments are in C, they have a tool for that, and you can use that to evaluate the code, look for certain things, and do some grading of them automatically. But if you don't have assignments that are in one of those two programming language, then you have to use the second method, which is to create a custom auto grader. And so that's what I had to do because my programming assignments were in VHDL and Verilog, which are hardware description languages for FPGA development. And so I had to create a custom auto grader. And in the Coursera world, this means that you have to have a program that runs in a Docker. Docker is a container which can be created and then destroyed at will within the platform. So every time a student submits an assignment, the Coursera platform will spawn a Docker. That Docker will have a program inside of it, which is the auto grader. That program runs, it creates some files and some feedback statements, which then get sent to the student by the Coursera platform. And once that is completed, then that Docker container gets destroyed. And so it's a process of creating containers, destroying them all the time. That limits then the amount of space that's used by their system in order to do the auto grading. And it also helps them manage, the amount of CPU and memory resources that they use in their system. So this is kind of the way that they've chosen to do it. And, that's a structure that you have to work with when you're creating a programming assignment auto grader on Coursera. So any questions about these two alternatives at all? Okay.
Wait, Tim, Cena
Yeah.
has a hand up.
Hey, Tim. So I was wondering if this Docker containers are run inside um, the Moog system that you're using. It's just, is it integrated in their system, or did you have to do a lot of work on integrating your containers with their system?
No, it wasn't too bad. You know, it's a part of their system. So all we had to provide them was the Docker file and the auto grader, which in our case is a Python script. And so that
Okay.
Python program runs into the container. The container gets created based on the description in the Docker file.
Okay. Got it.
And I'll show you the Docker file and some of the sample Python programs here in a minute, but they've got this all set up. I will say that there's not a huge amount of information about how to do this, and so it requires some interaction with some of their folks, and I was fortunate in that because what I was doing was a little unique. They assigned a programmer that worked at Coursera to kind of work with me in order to put this together. And so she did some of the work and provided some of the things, and I'll show you what those were, that allowed the Docker that was created based on our description to run in their system and pull out certain information from their system that our auto grader needed in order to make sure that, you know, it was the correct problem that was being submitted, that was being graded, and so on. So there's some details behind all of this that require some help and interaction with them in order to get that all to work.
Thank you.
All right.
Before you continue, maybe you're going to talk about this, but are
Yeah.
you going to, is there some step of the process that looks for copied code or prevents cheating in that fashion?
Yes, there is. And there's two different types of auto graders that we created. One was for the Verilog and VHDL assignments. And so there's some steps we took to prevent people from cheating and from submitting a copy that they got from somebody else and so on. There's also an auto grader for projects that are submitted. And that project information has, those files have some key things in it that we look for. And we look for certain things to try to prevent people from, like you say, duplicating code or you know, submitting you know, an exact copy of somebody else's assignment and that sort of thing. And so it should be able to catch those kinds of attempts at cheating. Having said that, there are probably ways in order to defeat what we've done, but you have to work at it so hard that it would actually be, I think, easier just to go ahead and do the assignment. And so that's kind of been the intent, is we make it so difficult that they just rather do the work anyway. So several stages were required to create this VHDL or Verilog autograder I'm going to talk about first. So initially what we tried was having the students submit the VHDL code or the Verilog code, and then inside of the Docker we'd have a grading program, which is basically a test bench that runs in another program called ModelSim. And even though supposedly there was a version of ModelSim that would run in the Docker is basically a headless Linux or part of a, what is it? It's almost like a Linux virtual machine, but it's actually a little less than that. We couldn't get it to run in the Docker. So we had a test bench that was going to be used to evaluate the code directly, and then reply, create some feedback that they would see. But we worked on this for several months, and we were never able to get ModelSim to run in the Docker effectively. And so we kind of abandoned this approach. So we got to think of a different way to do this. So we came up with an alternative that we would give the students the grading program and have them run it, and then report the results in an output file that's submitted. And then that output file would be parsed by a Python program, which would then generate all the feedback that the students would see. Now, if they could see what was in the grading program, then they could just create a fake output file, which had all the correct answers in it. And then, that assessment wouldn't have any integrity. At least that they looked at it fairly carefully. And so that the test bench for a Verilog submission is also written in Verilog, so they would know and understand what the test bench was doing. But as it turns out, ModelSim has a facility to run a test bench that's been encrypted so that they can't see any of the source code for the test bench. And so that's what we did. We leveraged the ability of ModelSim to run an encrypted version of the grading program test bench, so the students could not determine the correct output ahead of time. The output files that are generated by the encrypted test bench that could then be submitted, and those output files themselves are encoded in such a way that if you just look at them, you can't really tell what changes has been made as the test bench has run on their submitted code and then generated things inside the output file. The Python program that runs in the Docker then takes that output file, it runs through it, it looks through for certain information, it identifies errors in the output of their code, and then provides feedback for some of those errors. It also checks to make sure it's the right type of file, and that file came from a particular person and so on. So it uses a connection to the submission, so they know, who this came from and so on. We can kind of see that as we look at details of the example. So we learned a couple of things from this process. One is, don't be afraid to try new approaches while you're developing the autograder. We could have kept beating our head against a wall trying to get ModelSim to run inside of the Docker. I think we maybe eventually would have gotten that to work. But as it turns out, this works, I think, just as well. Although we had to use encryption to maintain integrity of the process, so it wasn't clear to the students what this test program does and what kind of output that it generates. And so when they submit the output file, they don't really have much of an idea what's in there, but we're able to look at it with the Python program and determine whether or not their code actually worked or not, and some details about it. We're attempting to replicate what we would do on campus, where we would actually look at the code, and read it kind of line by line and try to evaluate whether or not it would work, or we would actually run the code inside of the Quartus FPGA development tool and make sure it generated the right circuitry, because this is a hardware description language and that's the output of it. So we're trying to mimic that hand process. And so we can't look at every single source line of code, but we do look at the output that it generates, and we can check and make sure that the output is correct. And because of that, we are not forcing them to implement the code in a particular way. As long as it's functionally correct and gives the correct output, we'll be able to evaluate that using this auto grader. All right, so now we're going to take a look at some examples here. So this is an example HDL code submission. This is Verilog, and it's an example of a full adder. I'm going to switch over to an editor that I've got that highlights syntax in color for this particular language. So this module is a full adder. It has a couple of inputs that are 4 bits each, and also carry in, and then it produces a sum output and a carry out. So it's a simple adder. This is an example of what a student might do. It's a structural design, so they're using 4 single-bit adders in order to create a 4-bit adder and putting them all together. They could have done this differently. They could have done a behavioral description of the adder. They could have done a Boolean description of the adder. They could have done a data flow description of the adder. So there's lots of different ways in order to create logic using Verilog. As long as it created a working 4-bit adder, our evaluation of this would say that it was correct, and it wouldn't be particular to this particular kind of implementation. And I think that's a good thing. And so they would submit this particular set of code. And then we have a test bench that we would use. And so this is an example of the test bench. It imports their code as an instance of a component, and it does what's called an instantiation. So it includes that component into this test bench, and then the test bench has a bunch of looping primitives that it uses to create stimulus for this. And in this case, it's an adder. So we create all possible combinations of the A and B input, look at the added output to see if what it generates is correct. So we look to see if 2 + 2 gives you 4 in this particular case. When we're debugging, we had a bunch of display statements that we would look at. Those are not used when this is run by the students, so they can't see any of that. And then we create a ROM file where we put in some of the results. We have an error counter that we use. We determine where the first error occurs in the code. So we give them the line of code where their first error occurs if they have an error. And then we write this out to a file, which is called myvector.out. And so that's the file then that they would submit that would be evaluated by the Python program. What they see when they run the test bench is this. They see some aspects of it, but then at some point it's encrypted. As it turns out, ModelSim will go ahead and run this encrypted test bench just the same way as it would run the other one that I showed you. And it will produce the same myvector.out file. But obviously the students can't look at this and see what the test bench actually does. And so they can't kind of fake an output that would give you the result that you want. So they're giving a vector output file to use as an input to the test bench, and it produces this myvector.out. And so they submit that along with their code to the Coursera platform in their submission. And so this is what we're going to look at. And you can see it's just a bunch of hex numbers. But believe it or not, some of these hex numbers have meaning and some of them don't, based on the way the test bench runs and creates this file. So do we have any questions at this point about how all of this is working? Might seem a little too complicated, but this is kind of how we had to put it together to make sure that we could evaluate this fairly in a similar fashion to what we do manually, but also so that the students couldn't predict what the output was supposed to be.
So Wendy Martin is writing in, because she doesn't have a microphone, could she make this work with R and send the results to a vector?
Yeah, I think so. You know, the thing that is somewhat unique about this is that the simulation program that runs the test bench has the ability to use an encrypted version of it. You know, and so if your evaluation program can't disguise that in some way, you know, then the student would be able to see what it does. With R, you might be able to get an evaluation program to run in the Docker. You know, and if you did that, then you could have the students just submit the code directly. And then the program that evaluates it would run inside of the Docker and do that. And you wouldn't then necessarily need a Python script in order to do this. So, you know, that'd be a little more straightforward approach, I think, than what we had to do in this case, because we couldn't get Model Sim to run in the Docker. So, yeah, we've got an extra step in this that that for a lot of programming languages you're probably not going to need. So let me get.
Tim, I have a question for you.
Sure.
What if you do want to grade on an actual method, like rather than doing a really, computationally intense method, you want to do a more efficient method, and you want to be able to grade on whether a student implemented that?
Okay. I think there are ways to do that. It requires and we'll actually look at this in the project submissions that I did. Requires some foreknowledge of what those more efficient methods are supposed to be, and being able to evaluate whether they use that. So, you know, you could look at their submission and say, how many lines of code does this take versus whatever the optimal solution is? And so you could have the parsing program count those up. You could look for specific statements and for specific code if you wanted to do that, to see if this method required, I'm going to use a C example because it's a little bit of what I know. If the more efficient method required use of pointer to functions, you could look to see if they used a pointer to function, and you could evaluate that. You know, so I think it is possible to do that sort of more detailed evaluation of the source itself. In this particular case with HDLs, I'm not as concerned with whether or not they did it the very most efficient way. I'm just more concerned, is it functionally correct? Does it work? Can I verify that it works? And the thing is, the synthesizers are so efficient anymore. If you describe a certain amount of code several different ways, it will generate exactly the same circuitry as an output. You know, it kind of sees through all of that. So I don't have the issue maybe you have in more of a software kind of situation where you have some code that's going to be much more efficient. It'll be faster. It'll use less memory than other kinds of code. So I'm a little less dependent on the methodology maybe than other things would be. But when I get to the project auto grader, it actually looks and sees how much logic was used in order to create the solution, and it evaluates that. And if they require more logic than probably is necessary, then they actually get downgraded a little bit. So I have done something similar to that in a slightly different case.
Tim, if a student puts this through and gets the wrong answer. It doesn't.
Right.
What kind of response do they get?
I'll look at the Python program. You can see some of the things that we give to them. That's the test bench. So here's the Python example. I need to go back and grab that. This first set of things here, the part ID lookup, is something that comes from the Coursera platform. Sorry, I gotta find the where I put the auto grader. Oh, I thought I had that. Just a minute. So let me grab this back. So this is the auto grader program. The first thing that we do in this auto grader is we check to see that they've submitted the right file, because part of what we found was that the students would be working on problem 3 and then they would submit it under the problem 2 submission. And so our auto grader had to identify whether or not this file was for the right problem. And so the Coursera system has a part ID that's associated with every place where you make a submission. And so they gave us the part IDs for all of our submissions. And so we created a check for that to make sure it was the right file. So we had to know where the file that was submitted was, and it's in the shared submission folder. This is a path to directory that gets hooked into the Docker when the Docker is created. And so we can go to that directory in our Python program and make this check to make sure it's the right file. And if it's not, we say, you know, required output vector file not found, please submit all the required files. Or later on, we've got a message saying you submitted a file for a different problem, submit the correct file for this particular file, problem, and so on. So when we get down here, we look into the vector output that was provided, and we find out what the error count is, what their score was, where the first error was included, and so on. And then we give some feedback down here. If their score was a 10, in other words, we're grading this particular problem on a scale of 1 to 10. If it's a 10, great, your code is error free. That's the message they get. If they only had one error, hey, you only have one error. Several errors, review your code. If they have invalid output, then check to make sure you've got the right assignment and problem number, and so on. And there is somewhere in here where we tell them, I don't see it, but I know it's in here. There's a line where we determine what the first line is in their code that has an error, and say the first line of code that has an error is this line, so that they can jump to that and they can look at that particular line of code and know that that has some kind of a problem associated with it.
Excellent, excellent.
So, but a couple of the key things here. Yeah, this is where we're looking for that first error, but I don't see where we printed out the message, but I know it's in here somewhere. The things that we need from the Coursera system are these part IDs and to know that we have the right problem and we're looking at the right submission, and then access to where the submission actually exists. So I see you got a couple of questions on chat that are similar to that. The output generated always the same set for each test. yeah, so every student submits the same kind of submission. The auto grader runs on those and does the same set of tests and looks for the same set of errors. And however, although this Python script is looks at all the VHDL and Verilog problems that are submitted. So we just have one script, we have one Docker that runs for all the different problems. It sorts out which problem it is using these part IDs. Initially, we thought, oh, we're going to have a unique auto grader script for every single problem, and that would have been a pain. And in fact, Coursera was not happy about having to deal with that. So we have a single script that runs on all of the problems, you know, and so, but the test benches that we use in each case, which were given to the students, the test bench is unique to the problem. So half of the auto grader is the test bench. That test bench is unique to every single problem. And so we need a completely different test bench for every single problem. So that created a lot of work for us. In order to do this evaluation, I had grad students, once I gave them some examples of test benches, they were able to replicate those for the other problems. And so we were able to get all that work done. Now we use those test benches to auto grade the on-campus submissions. And so that's made the TA job a little simpler for the TAs for the on-campus class. You know, so it has some benefits, obviously, in both cases. You know, so that's how it kind of works. There's a single auto grader on the Python that runs in the Docker, but in order to create the output files, every single test bench is unique. All right, so let me get back to this. So this is an example of the Docker file that we submitted to Coursera that they use in order to spawn the Docker. The first thing that it does after it gets created, so whenever a student submits an assignment, the Coursera platform creates the Docker automatically. It just happens right away. They get feedback pretty quickly because of this. The first thing the Docker does is it brings in Python. You know, we're using 2.7. This is the slim version of Python. It's able to get that from a library that it has resident. It sets the working directory to a directory that's used. It copies the contents of the learner submission output file into this application directory. And then it runs installation of Python, does a command line command to enable permissions to be able to run the auto grader, and then it goes ahead and runs this Python auto grader that we've given to them on that, which generates all the feedback statements. Oh, I need to go back to the auto grader to explain how that works. So within the auto grader, we accumulate all of the feedback information, and it gets put into a format that is dictated by Coursera. Here, and it's down at this last line, where it puts the score and the combined feedback, which is a bunch of strings, into a JSON object. And that's when we do this print statement here, that puts then all of that feedback and the score, you know, they get for, in other words, their grade, into the Coursera platform. So that's how that happens, how that connection is made. Okay. And so when this runs, it finishes all that. And so when this is done, then they have a grade for that assignment, and they have a bunch of feedback statements that print out that they can see. So any questions about the creation of the auto grader for VHDL and Verilog at this point before I go on and talk about, oh, almost out of time.
Tim, for all these steps, do you contact someone there, or they have a web interface that you can just push these Docker scripts and stuff there?
In my case, I had a contact that I worked with. It probably took a couple weeks to get all back and forth to get this to work. I think they have better support on the website for that. They've got a number of, how to develop custom graders and things now. They've got more documents than they did at the time that I did this. And I think they expect you to do more of the work at this point, and don't provide quite as much help as what they did at that point in time. So you can expect you're going to have to do some of this, but there are some things that, like the part IDs, there's no way I can figure out what that is unless somebody from Coursera tells me and sends me that information. But I think it's a matter of sending an email to them at this point, and they'll assign that to someone who will get that information for you, and then it'll come back. Good question, though. It's an involved process that requires some help from them in order to get it all to work. So I also had in these project submissions, they create a project in a big development tool called Quartus and a number of project files. And so we want to make sure that they did the project correctly. And so we used to try to grade these things by hand, or then, look at the circuitry that was created. We found that we could use a Python program to look at these files, the log files or an output file that are generated by the tool, and do some evaluation of the project to determine if it was correct or not. And just the general idea of, if you have a program that they're supposed to write, and that program generates some kind of a log file or an output file, you can use that to help evaluate whether or not the program they created is correct or not. So these project files then that they created were submitted. They submitted a big zip file, so it's a number of files. It's not just one. The Python program goes through and looks at all those files. They have to put date and ID information into the submission, and that gets cross-checked to prevent duplicate submissions from other sources. So in particular, we look at the timestamp. It has to be within a certain range of when they made the submission. So if they borrow a set of project files from a friend that was done 3 months ago, this is going to catch that. They're not aware of the fact that we're looking at the timestamp. We don't tell them that. And so if they try to pass one off, that's going to be caught. Their student ID is part of this as well, and so we check that. Encryption wasn't necessary in this case. The project files are not really in a format that's human readable, but we have some idea of what's in there, and we can look at that. And some of the files are actually just text files that you can read if you know what you're looking for. And so this is an example of a project file submission for a tool called a fitter. It tells you how many logic elements were created in this particular example. And we know that if they do it right, it should have in the range of 500 to 700 logic elements. If they needed more than that, then they probably did something wrong. If they needed less than that, then they probably didn't do the whole problem. And so we check that and we grade it based on that. And we found that this is actually really effective in finding mistakes. But if they do it right, then this is going to pass it and give them a perfect score. This particular project file has a timestamp on it of when it was created. So we'll check that against their submission time. to make sure that, you know, this was generated about the time that they submitted it. Now, obviously they could have a friend that runs the project and creates this for them, and they submit whatever their friend submits. We don't have a way around that, but if they're the one that did the work, you know, as long as it gets submitted at the same time, then we're going to know that. If they try to submit something from somebody else from long ago that's already been graded that they know is going to get a good score, the timestamps are not going to match, and then that's going to get flagged, and it won't even be accepted. So it doesn't even get graded if the timestamps don't match. And then this gives you an idea of what's in the auto grader. It's looking at a number of different files and giving us a score for each one of those files, and creating the feedback line for each one of those files, so they get a little more feedback in this case. And then the last line here where it creates the JSON object to send back to Coursera is the same as it was before. But obviously this is 1,500 lines now of Python, so there's a lot more going on in this particular auto grader than there was in the VHDL version. That's partly because we don't have a separate test bench that's running on this. We're just looking at the output files themselves from the project, and that takes a little more work than what we had to do before. So so here are some conclusions. I know I'm running out of time here, and it's a Thursday evening now, and people may want to get going, but I'm more interested in answering any questions that you might have at this point.
Yeah, I
Hopefully-
have a question. It seems like some of the heuristics for the projects portion were specific to your language or your application, like
Yeah.
the number of things, I forget the word you used, but can you comment more generally? Do you think it's possible to be able to grade a project level assignment automatically always?
I do. I think this method has a general application. And in fact, another professor in our program who has created a specialization on real-time embedded systems, in a lot of the problems that he has students do, he makes them create a log file. And he does a similar sort of thing where he examines what's in the log file to make sure that you know, their program is running correctly, and he evaluates it that way based on that file. And I think you could generally do that. You know, security of that is a little tricky. I mean, I'm able to do some checks because of, you know, the way these files are generated by the tool. You would have to do something similar in any kind of other program evaluation where you created log files where you made them put the student ID number and timestamps and that sort of thing in it, so that you could do some cross-checking to try to prevent people from just copying outputs and sending those in as their submission. So there's a challenge there. And we're able to, like you say, achieve that security because of the very specific way in which our software tool generates output. That might be more difficult in some other cases, I imagine, but like I said, this other instructor uses, it's mostly just C programs that he evaluates, and he has them create this logging in a specific way, and then he's able to parse those log files and do grading based on that. So I think in general, you should be able to do that. Security of it is more of a challenge, I think. That's the bigger problem in my mind than just being able to evaluate things. I think you can do that. So I hope that answers the question.
Yeah, thanks.
So this is great. Tim, thank you. Thank you tremendously.
Oh, you're welcome.
I hope this was useful. I mean, I think the proof is in the pudding, and
Yeah.
it continues to serve pudding to thousands and thousands of students. So let's give Tim a hand. Thank you for taking us through this.